Hi, today we're going to talk about the Earth's interior. You're probably familiar with the concept of the Earth's interior being broken up into crust, mantle, core. And we'll talk about that. But there's actually two ways to describe the Earth's interior. One of them is based on what they're made out of. We call those the compositional layers. And it's kind of like saying a chocolate chip cookie is made up of flour and sugar and eggs and chocolate chips. The other way we describe the Earth's interior is by describing the physical layers based on their physical state of matter. So they're solid, they're liquid, or they're gas. Only there's not really a lot of gas inside the Earth's interior, and there's no layers of the Earth's interior made out of gas, but there is this weird thing that we just describe as plastic. And I'll get back to that when we get there. Let's talk about the compositional layers, because these are the ones you're actually familiar with. You've got the crust, the mantle, the core, which is actually inner core, outer core. Now the crust isn't that simple. There's actually two types of crust. There's oceanic crust, which is a very high density. It's made out of basalt, has a density about 3 grams per cubic centimeter, and this is found underneath the ocean floor. Underneath the continents, we have what's called continental crust. It's made out of granitic rock, and it has a density of about 2.7 grams per cubic centimeter. So it's a little bit less dense. And also, if you look at the diagram, you see that it's quite a bit thicker. Now, the reason oceanic crust is called oceanic crust is because there's an ocean sitting on top of it. Why is there an ocean sitting on top of it? Well, because it's thinner and it's more dense, so it sits lower in Earth's mantle. So those are the low spots of the Earth, wherever we have this basaltic crust. Below the crust, we have the mantle. Now, scientists don't really know a whole heck of a lot about the mantle. In fact, we don't really know a whole heck of a lot about anything inside the Earth. We know more about stars that are tens or 20s or hundreds of light years away than we know about what's more than 10 miles beneath our feet. Now the mantle we know is a little over 8/10 of the volume of Earth and about 7/10 the mass of the Earth, so it's gigantic. It's most of the Earth. Really don't know much about it though. Below the mantle is the core. There's an inner core and an outer core, and it's a good thing. The outer core is made of liquid iron and nickel. The inner core is made of solid iron and nickel. It represents about 1/3 of the Earth's mass, so even though it's relatively small, it's very, very dense. You'll see that the Earth's crust is very, 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 very thin, comparable to an eggshell. In fact, an eggshell is probably thicker, relatively speaking, than the Earth's crust is. So we live on a very thin, fragile, you could break it if you jumped on it real hard. All right, not really. The other way we describe Earth's layers are the physical layers. So this would be whether they're solid, liquid, or gas. So after we do some spinning, we've got the lithosphere, which is comparable to the crust. It's the solid portion of the Earth. We don't differentiate between continental and oceanic lithosphere. We just call it the lithosphere. Now you see in this diagram, there's a little bit of lithosphere below what we were calling the crust. The outermost layer of what we used to call the mantle is still solid. So you have what we used to call the crust and a thin layer of the upper mantle, which is also solid, that we refer to as the lithosphere because it is solid. Between the crust and the mantle, or if you prefer, the lithosphere and the asthenosphere, we have the MOHO. Now the MOHO is an easier way of saying the Mohorovičić, I'm pronouncing that wrong, discontinuity. This was discovered by, and it says Croatian seismologist, he was really a meteorologist, studied the weather. I bring this up because that's what I am. And we'll talk about a lot of geological discoveries that were made by meteorologists because they don't have enough to do because they're always forecasting the weather wrong. I'm kidding. So the Mohorovičić discontinuity is the boundary between the solid rock and the more plasticky rock. And it was discovered when Mohorovičić discovered that seismic waves were changing speed. If you've ever tried to grab a pebble off the bottom of a pool or a coin or your watch or something and you reach through the water, you know that light bends. At least I hope you know what I'm talking about. Seismic waves bend when they travel from rock of one density to rock of a different density. In this case, we're talking about solid rock into the plastic rock. So the seismic waves are bending, they're changing velocity. And that told him that there was something different. And there was a sharp contrast. It wasn't a gradual change. It's a very sharp change at a certain depth. Below that we have the asthenosphere. So this is most of the upper mantle below the lithosphere, and it's believed to be plastic. Now when I say plastic, I don't mean the stuff that your pen is made out of. It's a rock that it's not really solid and it's not really liquid. It flows extremely, extremely slowly. Below the asthenosphere is the mesosphere. This is the rest of what we used to call the mantle, and there's absolutely nothing interesting about the mesosphere. So we'll just take a big yawn, take a break. Okay, core. Now the core is where things get really cool. So the outer core, as I said before, is liquid nickel and iron, and it's circulating around the inner core. Now if you've ever seen a little electric motor, like in a toy, maybe it has an electric motor, what you'll see is magnets wrapped in copper wire. And when you get to physics in 2 years, you're going to learn about this. You can push a magnet through a coil of copper wire and generate electricity. Or you can push electricity through a copper wire wrapped around a magnet and make it move. So it works both ways. You can move it to make electricity, or you can use electricity to make it move. This is a very similar thing. We've got the liquid outer core moving, it's flowing because it's liquid, around the solid inner core, and it generates an electrical field. Electrical field, or magnetic field if you prefer, is what protects us from a lot of the charged particles that are emitted by the sun. Now you can occasionally see those charged particles emitted by the sun because at the north and the south pole of the Earth there's a hole in that magnetic field, and they kind of rain down toward Earth, and when they hit gases in the atmosphere they ionize and create light. This is called the northern light. So it's green, or it's red, and sometimes some other colors. And depending on what gases is exciting, it makes different colors. Green is nitrogen and red is oxygen. So those are kind of the two most common colors for the northern lights. You'll notice my diagram of the Earth, the bar magnet inside the Earth looks like it's wrong. It looks like south is towards the North Pole, north is towards the South Pole, and that is actually the way the magnetic field of the Earth is aligned. The inner core is just a solid ball of iron and nickel. We think. And this is all speculation. Why are we speculating? How do we know any of this? Well, we probably drilled a hole, right? We all know we drilled deep. Oh, no. No, that's not it. The Russians have actually drilled the deepest hole. There's a picture of it. It's very exciting looking. They haven't done much there in the last 10 years or so, but the Kola super deep borehole, they got to a depth of about 7.5 miles, and that's the deepest we've ever gone into Earth's crust. We've never gotten anywhere near the mantle. They estimate that this is about 1/3 of the way through the crust. So that's as far as we've gotten. And the problem is, once you get to a certain depth, the rocks get hot and they start to melt the drill bit. And once the drill bit gets to be a certain length, it starts to twist. It's just too long to turn, and the metal twists instead of the drill bit twisting. So how do we know what's inside the Earth? Well, go back to the MOHO. We know from refraction and the absorption of seismic waves that there are different layers of the Earth. Also, by looking at the composition and structure of some meteorites that we've found, scientists can estimate approximately what the Earth is made of. So based on the speed of seismic waves, they can tell density, and from meteorites they can tell composition, and when you combine our knowledge of composition and density, you can get an idea of what the temperature of the inside of the Earth is. That's it for today, and I'll see you in class next time.